Hello everyone, my name is Jibitesh Chakraborty, and in this lecture we'll be seeing how can we make our very own photo to sketch generator using autoencoders. Right. Now let us just exactly see what do we exactly aim to build. So you can see like there are pretty much available online sources like this one where you can like upload any image and it creates a pencil sketched image out of it. Let us see how it works. We will upload our own image. Let's say I upload this image. If I hit this button, it will generate a pencil sketch out of it, right? Okay, so this is the exact goal of our project that we are going to target. Now let us understand what an autoencoder is and what like how an autoencoder works, like the architecture of an autoencoder, right? Now going back to the slide, if we like see the autoencoder architecture, we can see that an autoencoder takes an input image and has an encoder layer which compresses the image into something known as the latent space. Now, what is this latent space? This latent space is basically a compressed version of the image which only holds the relevant information related to the image. Now, these relevant image like information can only hold like a few of the pixel values which are absolutely important and capture all the information related to the image, and from that latent space, which is the bottleneck of this architecture, from that like latent space, my decoder basically reconstructs the image that I want to generate. So this is exactly how an autoencoder works, and it works like perfectly for like applications where you have an input image and you want another output image, which is basically another form of the input image, right? Now let us have a detailed code walkthrough of how I can actually build my very own photo to sketch generator, right? Okay. So before we actually get there, I'll be showing that I have got this data from Kaggle, which consists of normal images, and it also has its corresponding sketched images, correct? See, these are the sketched images. Now, what we want to do is that we will be using the normal images as the input and the sketched images as the output, which is pretty much obvious from our application, right? So what do we do first? First, we need to import in all the necessary libraries that are required, right? Once we are done with that, we need to make sure that our Google Drive, where our data is stored, is mounted on our current session of our Google Colab notebook, right? How do we check that? There will be a drive folder in our like file section, and then if we like go down, we'll be having a my drive folder, and inside your my drive, you'll be having all the like data of your Google Drive, your current Google Drive, right? Once you have that, now we are good to go with the work, right? First that we need to do is that first we need to get all the images in a list, right? So basically what I will do is that when I write os.list dir and then the URL of my uh, folder where my normal images are, what it basically does is that in this folder, this is basically the like relative path of the folder in which all my normal pictures are stored, right? When I write os.list_dir followed by this relative path, what it basically does is that it takes everything that is inside the normal folder and stores it in this list called normal, right? So this normal is basically a list holding all the images which are in the normal category, correct? Then I do the same with the sketched images. I have a like list of like I have this folder sketched which stores all the like contents of like all the sketched images, and it is stored in this sketched folder, correct? After I'm done with that, I'll be doing normal equals sorted normal. What this statement does is that it basically sorts all my images based on the name of the images. Why am I doing that? So that I do not really have any discrepancies in my normal and sketched. Like if my first image is first index of my normal list contains the first image, then the like the first index of my sketched image should also contain the sketched version of my first image and not any other. That is why I'm writing normal equals sorted normal and sketched equals sorted sketched. So this is basically importing, this cell basically imports all my images, right? My input image and my output images, correct? Once we are done with that, now let us get into the processing part, right? Okay, so we are pretty much familiar that for input, we like denote all our input with x's, right? And we denote all our outputs as y, correct? So x is my input, y is my output, right? It is pretty clear. So what is my x? My x should be a list of images. But then you may be asking that I could have simply taken my normal list and like denoted it as not like x. Like why am I like creating a new like list called x and a new list called y? The reason being, this list x and y is basically going to store my pre-processed image. Why is pre-processing necessary? Pre-processing is necessary so that I can make the dimensions and the pixel values in a consistent format, because consistency is the most important for deep learning or any machine learning like paradigm. Like if you are making a machine learning model, it needs to have data which is absolutely consistent and not inconsistent at all. So consistency is of utmost importance when you're working with deep learning or machine learning stuff, right? Okay, so first I like create an empty list called x, and then I create an empty list called y, right? Then what I do, I traverse from I equals from I in range 0 to 300. Why do I do that? That is because my data set contains around 300 to 350 images. So it is a good bet if I just go with 300. And honestly, 300 images are good enough for training this like model. We'll be going further with the code, and we'll be seeing that exactly how 300 like images are exactly like enough. I don't need more than that, right? So just for checking in which iteration we are, I'm just writing print I plus 1. This gives me an idea in which iteration of the loop we are currently in, right? Then what I want, you remember this normal basically holds what? My basically holds the file names of my normal images, right? So when I write f is equals normal I, what it does is that it takes the ith indexed normal image out of the list normal. Then what I will do is that img equals cv2.imread. What does this do? cv2.imread basically reads an image, right? What is cv2? cv2 is basically the abbreviation for OpenCV Python, the library which is used for working with images in Python, right? So when I write cv2.imread, I'm basically reading an image. But when I write cv2.imread, I need to pass the path to the file, like the image file that I want to read. So how do I get the file path? Over here, I am getting what? I am getting the name of the file, but I'm not getting the entire file path. Then what should I do? I should be joining this, my folder path, with my file path, with my file name. Like what is it? Like first my folder path comes in, and inside that I have my file name. If I do that, that's when I have the entire file path, right? That's exactly what I'm doing. When I write os.path.join, I'm telling that I have a path which I want to join, right? Then what do? I first send my first initial path. What is my initial path? My initial path is my like relative folder name, like my folder path, right? This is my relative folder path, which is my normal folder. And with that, what do I want to join? I want to join the file name. So I pass f. So what does this do? os.path.join followed by the folder name and then followed by the file name. This gives me a full like connected path to the file, right? Now this file path is being passed to cv2.imread, right? And as soon as cv2.imread is getting the file path, what it will do? It will basically extract the image from that file path, correct? So now img has the image, correct? Once img has the image, now what do I want to do? I want to bring my file, like my images, to a certain dimension, a consistent dimension, right? So the dimension that I am right now considering is 128, 128. Why am I going with 128, 128? That is because it is not a very big dimension and is pretty easy to work with, and it does not cause much, like, does not require much of computational power. But if you are willing to go with higher dimensions, and you want really HD images, then you can go with higher dimensions. But you need to make sure that your dimensions are not very high, which requires massive computational powers, right? So yeah, 128, 128 is a pretty good like resolution, or like high, like good dimension for an image to work with. So when I do img is equals cv to the resize, what does cv to the resize do? It basically takes an image and brings it to a certain dimension. I resize it to a certain dimension. What dimension am I passing? I'm passing 128, 128, right? 128 pixels and 128 pixels, like row wise 128 pixels, column wise 128 pixels, correct? And what do I want to resize? I want to resize my image. So I also need to specify what I want to like resize. So I'll be passing img2. Now I'm writing something new. What is that? Interpolation equals cv2 dot inter area. Why is this required? This is required because I want to specify, I want to tell that do not cut anything from top or bottom. Keep everything, keep the entire image, like keep the entire image intact, but just compress it in such a way that it comes in this like specific dimension. That is why I need to mention interpolation equals cv2 dot inter area. Because if I don't do that, what it might happen is that it might cut it from the top or bottom or somewhere from right, left, and like basically to keep the area consistent. Like, what is the area? The area should be 128 multiplied by 128, right? So this 128 comma 128, this like area, it can cut it out from anywhere in the image. I don't want that. I want my entire image to be intact, right? That is why I'm writing interpolation equals cv2 dot inter area, so it does not cut out anything, any portion of the image, and keeps the image absolutely intact, right? Okay, so what does this statement do? Let us have a recap. This statement basically resizes my images to a certain dimension, a consistent dimension, that is 128, 128. But we also need to remember that this is a colored image that you are working with. So there will also be 3 channels. So now my image has, what is the shape of my image? 128 rows, 128 pixels on the rows, 128 pixels on the columns, and 3 color channels, like BGR color channels, correct? Yes. Now, once my resizing has been done, what do I want? I want the pixel values to be consistent. Why do I want the pixel values to be consistent? Because as I mentioned, if you're working with any deep learning or machine learning model, you need to keep the entire value set, like the data set, absolutely consistent. Every value in the data set consistent. So for that reason, we want this, like every pixel in the image to be like reduced to a certain, like not reduced to a certain, like brought to a certain normal form, right? This normalization that I'm executing is known as the 0-1 normalization. Why is this called a 0-1 normalization? Because after I execute this statement, all the pixel values in my current image, which is stored in img, is basically brought down to a value between 0 and 1, right? It does not like change my image in any way. You will be getting the same image whatsoever, but only that my pixel values will be between 0 and 1. That's it, correct? Once we are done with the processing of each and every image, what do I want? I want to add it to my X list. What was my X? My X is basically a list of all inputs. And this IMG holds one specific input for my ith index, correct? So I want to append that in my X list. So I'm writing x.append img. What does this statement do? This statement adds my current image into the X list. Perfect. We are done with our X's. Now let us get to our Y's, like my outputs. Now what do I want? My I was iterating from 0 to 300, correct? So it will obviously have a certain like index, right? I basically is holding an index starting from 0 to 299, correct? That is because we are like running from 0 to 300. So it's basically iterates from 0 to 299, right? Pretty much cool, right? Then if I write f is equals sketched I, what does this give me? This gives me the file name of my ith indexed sketched image, right? Initially we were seeing normal, now we will be seeing sketched, right? After we have got the ith file name of the sketched image, we will be extracting that image by joining it with our sketched folder file path, correct? So we will be again writing cv2.imread followed by os.path.join, and then we will be passing the folder name sketched and then the file name, which is we are denoting as f, and this f is basically my ith sketched file name, correct? After we have extracted the image using cv2.imread, we will be resizing it to a specific dimension, correct? Now, what is the dimension that we are again dealing with? Here we are dealing with a 128, 128, correct? And we will be keeping the interpolation as cv2.interarea so that we don't have any loss in data or loss in image, correct? Then again, what do I want to do? I want my image to be like my pixel values to be in a specific range, which is what is my range? My range that I'm considering is 0, 1, correct? So this 0, 1, like my output image is also in the range of 0 and 1, correct? So my input is input image is of the dimension 128, 128. My output is of the dimension 128, 128. My input is of my pixel values are in the range 0, 1. My output pixel values are also in the range 0 and 1. So you see both are consistent, correct? Now once my output images are sorted, I will be adding that to the Y list. So my Y list now holds all the images of my like pre-processed images of my outputs, correct? Now once that is done, my data pre-processing is absolutely complete, right? Now let us go down, and now what do I want is I want x was initially just a Python list, but now I want to convert it into a NumPy array. That is, since we are working with a machine learning like project over here, we want to work with NumPys, right? NumPy like is the library for working with numeric Python arrays and lists, correct? Like it makes a lot of like computations pretty easy. Like yeah. So x is basically x. Now I'm converting x into a NumPy array. So I'll write x is equals to np.array x. Why am I writing np? Because I had imported NumPy as np, correct? Over here you can see import NumPy as np. So we had imported NumPy as np, correct? So when I write x is equals np.array x, it converts my x, which was just a normal list in Python, to a NumPy list or NumPy array, right? I do the same with our y, which is our outputs. I write y is equals np.array y. So what does that do? It basically converts my y to like my outputs to a NumPy array, which was initially a normal Python list, but now it gets converted to a NumPy array, right? Now let us see what is the shape of our x array. X dot shape. It gives us 300, 128, 128, 3. What does this tell me? What does this tell me? It tells me that I have 300 images. This 300 images the number of images that I have, right? This 300 denotes what? The number of images that I have, right? Followed by 128. What does this 128 denote? My 128 denotes the number of rows or the number of pixels in the horizontal direction of each image. What is that? 128. So each image has 128 horizontal pixels, has 128 column wise pixels. Sorry, these are vertical, these are horizontal. Let us just go row wise, right? Like 128 pixels row wise and 128 pixels column wise, right? So that is why 128, 128. The first 128 denotes rows, the second 128 denotes columns. And what does this 3 denote? This 3 denotes the color channels, right? Since we are dealing with colored images over here, this will obviously have 3 color channels. What are the 3 color channels? They are R, G, B. What is R? R stands for red, G stands for green, and B stands for blue, right? So RGB channels. These 3 channels, when I overlap, like if I overlap all these 3 channels, I get a image, correct? Now if I again see y dot shape, I again get 300 images. Then I have 128 row pixels, 128 column pixels, and 3 channels, correct? So my data dimension wise is now absolutely consistent, correct? So I have, at least right now, I have verified that my dimensional consistency is absolutely taken care of, correct? Now I need to see, are my pixel values in the specific range, like what I wanted them to be. So I will just simply write x dot max. What does x dot max tells? X dot max like finds out the maximum pixel value in all the images that are present, right? So that gives me 1, right? So the maximum pixel value that I have in my input images is 1. And what is my minimum? I'll again find it, x dot min. It will give me 0, right? So you see, for our input images, all the pixel values have also been brought down to a consistent value, like range from 1 to 0, correct? Now let us see for y, our output. Our output, if I want to see what is our maximum pixel value, I'll again write y dot max. Y dot max also gives me the value as 1. Wow. So what does this tell me? Over here it tells me that all my output image pixel values are also brought down into the range of 1 to 0, correct? Now if I see what is the minimum value in our output, that I'll see by y dot min, that gives me again 0, right? So my range is between 1 and 0. Perfect. Now that my consistency or my pre-processing has been successful, like once that has been verified, let me see how do the images look like. I'll just write plt.imshow x50. What is PLT? PLT is the abbreviation for matplotlib.pyplot. Like if you remember, we had imported matplotlib.pyplot as PLT for our own benefit, right? So that every time I have to use matplotlib.pyplot, I'll simply write as PLT, and this PLT will point to matplotlib.pyplot. And what is matplotlib? Matplotlib is basically the library of Python which is used for plotting out images, graphs, like diagrams, whatever, right? Like all plotting kind of things or display kind of things are basically done by Matplotlib, pretty much. Okay. So if I write plt.imshow, what does imshow do? Imshow displays an image. So what do I need to pass to imshow? I need to pass to imshow a like an image. And what is an image? An image is basically a matrix, right? So I need to pass to imshow a matrix of pixel values. So let's say I want to view my 50th, like a fifth, not 50, this is the 51st. So like I want to, let's say I want to like view my image at my index 50 in my input array. So I'll just write x50. So that basically fetches my 50th index image, and I'll be passing it to plt.imshow, and that will be giving me what? It will be showing me the image at the 50th index, right? So if you see, this is the image which after pre-processing is our input at the 50th index, correct? Now let me see the output, right? So plt.imshow y50 shows me the output image at the 50th index. So this is my output in my 50th index, correct? So you see, if I put this input, I should be getting this kind of an output, correct? Now comes a very crucial part in any machine learning project, which is called the train test split. What does the train test split do? Whatever data set that I have, right, can be any data set whatsoever, it basically splits that data into training set and testing set. Why is this done? I will basically use my training set to train my AI model, and then I'll be using the testing set for two purposes. The one purpose is to track the like testing accuracy, or how would the like model performs on like unknown data, like data which the model has absolutely not encountered in the training procedure. And one more thing, that is validation. What is validation? Validation is something that is more into the depths of machine learning and deep learning. If you want to like want to know more on validation, you can of course contact us at FafTutor. At FafTutor we do have our boot camps, and we have tutorials, one-on-one tutorials. If you want to take a boot camp or a one-on-one tutorial, you can contact us at FafTutor. Over there, we do like work on boot camps on tutorials on deep learning and machine learning and data science as a whole too, right? So basically, the train test split basically splits my data into two segments, my training segment and my testing segment, right? So if you uh, this code, basically what I'm writing is from sklearn.model selection input train test split. This train test split is basically a module present in my library sklearn. In sklearn, sorry, this is not the module, this is the function train test split, and the module that I'm importing is model underscore selection, right? So from sklearn library, I'm importing the model underscore selection, and this model underscore selection module has this function called train test split. This train test split is basically the function which is used to create these segments, the training segment and the testing segment, correct? And what is the syntax of writing the train test split? I need to mention where do I want to store my training segment of my inputs. So I will write as xtrain. Xtrain holds the list of all training images of my x, like my inputs. And xtest holds all the testing images of my inputs, right? What does ytrain hold? Ytrain holds all the images belonging to the training segment of my outputs, and ytest holds all the images of my testing segment of my outputs, correct? So you just need to, you definitely need to follow this order: first xtrain, then xtest, then ytrain, then ytest, correct? Okay, now what do we need to write? We need to write train test split. What are we calling? We are of course calling the train test split function that we just imported. And what do we need to pass? We need to pass the entire data set. What is our data set comprised of? Our data set is comprised of inputs and outputs, basic. So my inputs are my x, my outputs are my y, correct? Okay, control Z, yep. Control, sorry. Uh, my x is my inputs and y is my outputs, correct? Okay, once my inputs and outputs have been specified, I need to specify what will be my testing size. Like what percentage of my data, what percentage of my entire data set do I want to treat as testing segment. So I will mention that test size equals 0.3. If I write 0.3, it basically means that 30% of my data is being considered as testing and rest 70% will be treated as trading, correct? And then I am writing random state equals 42. What does this do? Random state after and the value mentioned above after it basically reshuffles the data set in a random order. Why am I doing the reshuffling? I'm doing this reshuffling so that my data set remains consistent throughout the data set, like throughout the training process, and it is not um after it should not follow a certain pattern. Like if there is any pattern in the data set, like if my data set is sorted in a certain pattern, I want to break that pattern so that my machine learning model, my deep learning model can get into the underlying features and not follow any pattern of my data. So that's why shuffling of the data is very important, right? So like I'm shuffling the data. After this train test split has been done, let me just check how many are my training images and how many are my testing images, right? So if I write x test dot shape, it will tell me exactly the shape of my training segment. So my training segment has 210 images and then the details of each image, that is 128, 128, 3, correct? And my test segment has 90 images. So 90 images for testing and then followed by the image details, correct? Then again for my training, the output images will also be 210, right? Training outputs are 210 images and then followed by 128, 128, 3, which is basically the image details, like 120 pixel row wise, 120 pixel column wise, and 3 channels, right? Again, I have 90 images for testing and 128, 128, 3 as the image details. Okay. Now that my train test split has been done, now we are going to build what? We are going to build our very own autoencoder, right? This is the autoencoder code that we are going to study. Now, before we proceed with this code, it is good that if we recap the architecture once, right? So, if you see this architecture, remember we had an autoencoder section. So, sorry, we had an encoder section. What does this encoder do? Our encoder takes the input image and basically compresses it to something which is known as the latent space, correct? It compresses it down to this latent space, and from this latent space it will again reconstruct this image to create our new image, correct? So what are the two things that we need to build? We need to have an encoder and a decoder, because this latent space representation is not something that is in our hands. This basically compresses it and forms a smaller image, which is we are like telling as the latent space. But this latent space is not something that we will be defining by ourselves. We will be defining the architecture of the encoder and the architecture of the decoder, correct? So let us just see that. Okay, so what are the things that we need to import? First, we need to import from tensorflow.keras.models, import model. What does this do? It is pretty obvious that we are going to build a deep learning model, and it will obviously be denoted as a model itself. That is, and the deep learning library that we are using is TensorFlow. So inside TensorFlow, we have Keras, and in Keras, we have this module named models, which has this like very nice class known as the model class. This class model allows me to build any model that I want, right? Okay. Once my model has been imported, I now need to import what? The layers. Every deep learning model has layers. It can be a convolutional layer, it can be a recurrent neural network layer, it can be a dense layer, it can be any layer whatsoever. Over here, we are of course working with convolutional layers, max pooling layers, and upsampling layers. But when we are working with normal neural networks, like fully connected neural networks, we'll be dealing with like dense layers. And when we are working with time series data or natural language processing, we'll be working with what? Recurrent neural network layers, correct? Like LSTM layers, GRU layers, and all those, right? Okay. Now let us get deep into the code of the autoencoder, right? The first thing that we need to define is our input layer, right? So input equals input, and then we pass the dimension. So what does this statement do? This statement basically creates an input layer for me, right? Okay. Now this input basically holds the results of what? The output of this input layer, right? So what is the output of this input layer? It is basically the input, it is basically the image that I'm inputting, correct? So now this input holds what? My input image. Okay. Now I'm writing output equals conv2d followed by filters 64, kernel size 3,3, activation 10 inch, padding same, and then followed by I'm passing a parameter input. So what is conv2d? Conv2d is basically a method which basically denotes which layer, the convolutional 2D layer. And over there I'm passing what? 64 filters. What are 64 filters? 64 filters as basically the filters of our convolutional layer that we'll be using. So over here in the first convolutional layer, we are working with 64 filters. And what is the size of each filter? And specifying the size of each filter is 3,3. So three rows, 3 columns, correct? If you want to get again into the depths of convolutional neural networks, you can again book a session with us at FabTutor, or you can just like take our data science bootcamp. Over there we cover entire deep learning and machine learning and everything, and we get into the depths of convolutional neural networks, recurrent neural networks, and a lot of other stuff. So you can like definitely you should check it out, like if you want to learn, right? And what is the activation that we are working with? The activation that we are working with is 10 inch. And why do we write padding equals same? We write padding equals same so that our output image is consistent with our input image, right? So I am telling that if my input for my current convolutional neural network is 128, 128, 128, like 128, 128, like rows and columns, my output should also be 128, 128. I'm keeping that consistent as of now. So I repeat this, like I keep repeating the same layer. Just the thing that we need to note is that initially my first input was for my first convolutional neural network's input, which is basically the output of my previous layer. After that, for all the layers that I use, my output is basically, my input is basically the variable output, which is holding the output of my previous layer. So this output denotes this output, correct? Again, this output denotes this output, right? So what do? We keep repeating the convolutional layers for how many times? 5 times. We have 5 convolutional layers followed by a max pooling layer. Why do I use this pooling layer? We use this pooling layer because if you remember, we had to create a latent space, a smaller compressed image. So what does my pooling layer do? Our pooling layer basically compresses our image to a certain dimension, to a certain smaller dimension. Our convolutional layer could also do the same. In fact, it does the same, but since we are keeping the padding as same, we are not compressing anything on our convolutional layer. We are just processing the images as we go through the convolutional layer, but we are not compressing it. The compression is done in the max pooling layer, right? After my max pooling layer is compressed, right? Like after my max pooling layer compresses my processed image, I will use the upsampling 2D layer to again increase the dimension. Like basically my, as of now, since all my padding was same, as of now till here, till this output, like this layer's output, everything was 128, 128. Nothing was compressed, right? After here, but after this layer, it gets compressed down to 64, 64. Why is it 64, 64? Because my pool size that I'm working is 2, 2, right? What does 2, 2 indicate? 2, 2 indicates is that whatever is my current input, just half the size. Had my pool size been 3, 3, it would have like divided it by 3 and not halved it, right? So 2, 2 halves it, 3 by 3 divides it by 3. If I write 4, 4, it divides it by 4. So I don't want to compress it too much. I'll just I'll just half the thing. So that is 2 by 2, right? 2, 2. So since I'm halving it down, I need to again multiply it and make it bigger. So that's exactly what my upsampling 2D does. And I'll mention size as 2. Why am I mentioning the size as 2? That is because my pool size is 2, 2, and now my upsampling size is also 2, 2, right? So over here, my compression is complete. My upsampling or getting it back to the dimension is also complete, right? Now what I need to do? Now I need to reconstruct the image, which is done by the following 5 convolutional layers, right? And mind you, I'm using all the activations as tan-inch, 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 right? But, but if you see my last layer, has filters 3, kernel size again 3, 3, and activation is sigmoid. Why do I have this? I have this because remember our output image also had 3 channels. If you see our Y test or my Y train had 3 channels. So it is not just the row dimension and the column dimension that we need to be like concerned about. We also need to be concerned about the number of channels. The number of channels are 3. So my output image should also have 3 channels. So if I write filters 3, it basically gives me a 3-channeled output, right? And why am I mentioning activation is sigmoid? Because again, if you remember, our output image also had our like pixel values normalized in the range 0, 1. And what does the sigmoid activation do? It generates like results all in the range of 0, 1. Correct? Perfect. Once this series of layers is complete, I need to create my model, right? How will I create my model? This I'll be calling model equals model. This model is basically an object of this model class, and this model class takes inputs. What are my inputs? My output of my input layer, this is basically my inputs, correct? So I'll pass inputs equals input, and then I'll write outputs equals output. Why? This is my final output, right? This is my final output, and this is exactly what I want as my result. So I will all when I write outputs equals output, it takes this as the output and it takes this as the input. So I'm telling that start inputting from here and give my output over here, right? So that's exactly what I do when I write model equals inputs equals input and outputs equals output, right? And now I need to write model.compile loss equals binary cross entropy. Why am I writing binary cross entropy? Because this loss, this binary cross entropy loss, basically checks each and every pixel value loss and checks how close it is to my actual output, right? And the metric that we want to monitor is accuracy, right? That's why we write metrics equals accuracy. Okay, now to see that my model has been created or not, I will just run model.summary, and this exactly summarizes exactly what are my inputs, like inputs to outputs. So if you see, you remember we were taking inputs in the shape of 128, 128, 3, and it was processing, and then it was giving an output again in the like dimension of 128, 128, 3. So we see our dimensionality has been conserved. Correct. Now comes a callback. What is a callback? A callback basically monitors your loss on my validation data. You remember we had mentioned that for testing data also has a second purpose, which is called validation. Validation is basically checking consistently after every iteration of our training, like after every epoch, that what is my loss on my testing dataset or dataset which is not seen to be like model at all. So that is what validation does. So what does validation help? Validation basically helps in my model from overfitting. Like it does not, like it prevents my model from going, like it basically prevents overfitting, right? So that's why I need to like specify a callback. And over here I am specifying a callback as early stopping. So what does early stopping do? Like what does early stopping does do is that if I have mentioned epochs, let's say 1000, and it sees that after 20, like or 30, or let's say 200 epochs, after that's 200 epochs, my model starts overfitting. So it will just see that it will wait, as I've mentioned patience as 5, it will wait for 5 epochs and it will check that is it actually overfitting. So if it sees that after 200 epochs, yes, my model is actually overfitting, it will only wait till 5 epochs and then it will stop the training totally, right? Okay, so once that has been done, I will basically put my model into training. So how do I do that? I'll write model.fit, then I'll pass xtrain, then I'll pass ytrain, then followed by I'll be passing my validation data, which is X test and Y test, and then I'll be mentioning epochs as 500. I'm considering that maybe 500 will be required, though because I have no really damn clue like how many epochs it will take. It can take up to total full out of 500. It might also take up to like just somewhere around 100. So that's why it is a good idea you give a higher number of epochs and just mention early stop, like specify early stopping so that it just stops. And what then we need to mention what is our callback. Our callback is basically early stop, right? Okay, so we saw that our model just required 6 epochs, and beyond 6 epochs it was giving us a pretty good loss. I'll tell you, please do not go by the accuracy of your model, and your accuracy is not a good measure on how your model performs. Your loss is a good measure of how your model performs. We can see that the accuracy on our testing is just 35%, we can see, but our loss is also very less, right? And when we see the actual results, you'll be seeing that the results are actually very good, right? So if I write y res equals model.predict and then I pass x, what it means is that it takes the entire data set, my x, and it like what and it like takes that as the input and puts it to my model. My model predicts the output and gives the result and stores it in the like y underscore res list, right? So my y underscore rest holds my results, correct? Okay, now let me see my output for my 50th position result. So if I write plt.im show yrest50, it should give me the like my output for my 50th. So if you see, this is the image that we are getting as the result, right? Now let us go back to the actual image that we had. This is the image that we wanted to generate, and this is the image that we generated. So you can see our model is actually working really good, right? Like if you see the results are just fabulous, right? Okay, so now that my model is ready, I want to save my model. So I'll just run model.save, and then I'll be passing the relative path where I want to specify or store my model. Mind you, since it's a deep learning model, we will be storing it with a .h5 um, extension, right? So the .h5 extension basically stores deep learning models using TensorFlow, right? Okay, since model has been saved, I want to see that has the model actually been saved and has there been any problems in our saving. So I'll just write from tensorflow.keras.models import load model. Now this load model is basically a function which belongs to the module models, and in this load model function I need to pass only the relative path of my model that I have stored. So if this was the relative path to the model and the model name was photo to sketch.h5, and if I like mention exactly this path, I should be getting my model, right? Okay, so if that is where my model is stored, so if I write new model equals load model and then followed by the relative file path, I should be getting the model back. That exactly what happens. I get back the model. How am I verifying it? If I write new model.summary, I'll be getting exactly what was written, like the model details, what was written previously when I had run model.summary. If you compare model.summary and if you compare new model.summary, it is exactly the same thing. So my model has been saved successfully. Okay, now let us check on a pseudo image, like the image that is totally not in the dataset whatsoever, an image which was never taken from any source. It was just a random image that I pulled out from Google. Let us see how it performs on a like how our model performs, right? So the image that I'm working is this. This is the image. It is the image of a choco chip cookie, right? I will be taking this image, I'll be processing it, I'll be feeding it to my model, and then I'll be generating the result, and then I'll be displaying the result. So let us see the steps involved in there, right? Okay. So first that I need to do is I need to like import my image. I'll be writing image equals cv2.imread followed by the relative path of the file, right? So it was in my drive folder, and in this like photo to cartoon folder, inside that I had chocochipcookie.jpg. I import that using cv2.imread. Followed by that, I resize the image. Like I had mentioned, the first step was resizing. So I resize it to 120 to 128, and I will write interpolation equals cv2.interarea, correct? So what does cv2.interarea do? It basically compresses my image entirety and does not cut it out from anywhere, correct? And then what I need to do is I need to like I need to normalize my pixel values within the range of 0 and 1, right? So that is exactly what I do. My image gets normalized in the range of 0 1, right? And then what I want to do is that I want to visualize my image after pre-processing. So after pre-processing, my image looks like this. Now you may be seeing that why is this image like in blue and something else, and blue and white, right? This is because this is the problem of Google Colab. If you run this on Jupyter Notebook on any other source, you will see the exact color is preserved. It is just the problem of Google Colab. That's why it shows in blue, right? And if I see what is my image shape is 128, 128, 3, right? But the thing is that before I send it to my model, I need to add another row before it. Why am I doing that? Because what TensorFlow does is that it discards rows. Like it will always think that my data is inside a row. So my first row, like my first entry point should be a row. So I'm adding a extra row, and within that row I will be adding my image. So if I write image equals np.reshape image followed by 1 comma 128 comma 128 comma 3, it is basically putting my image in a row in a specific list, right? So image is basically a list storing only one specific image, correct? So if I write res equals new model dot predict image, I will be getting the resulting image, correct? So basically res stores a list storing only one image, which is basically my result. So if you see the shape, res.shape, I see I have an extra row followed by the image, right? So I need to remove of the row. I won't need to take out the image out of the row. So I will just write res equals np.reshape res 128, 128, 3. What does this do? It basically takes out the image what was inside the res list, and it is storing in res variable. So now res just stores the image, right? So if I write plt.im show res, it basically gives me this sketched image of the cookie that I wanted, right? Now this was the code implementation, correct? Now what if we want to make a web application out of it? So for making a web application out of it, we will be using Streamlit, right? So for that, what I need to do is I need to connect my notebook to a runtime, correct? So I'm connecting my runtime, right? It might just take a moment. And my Google Drive is being mounted, as you can see. Once all these steps are done, like we'll be good to go, right? And yes, my Google Drive has been mounted and my runtime is connected. Great. Okay. Now that everything is ready to go with, let us just start. Okay. So first thing that we need to do is basically install Streamlit in our current runtime. What is our current runtime? Our current runtime is Streamlit, like my not Streamlit. Our current runtime is this Jupyter notebook of Google Colab. So I need to install Streamlit over here. So if I run this, okay, okay. So pretty much Streamlit gets installed. Okay. Now what do I need to do? I need to get the IP address of my current session on my server machine, right? Yeah. So this basically gives the IP address of my current server machine. Now what I need to do is that I need to open up my Streamlit application where I have written, right? Okay. It is basically inside my photo to cartoon folder, and I call it as streamlit app.py. So if I just, yeah, if you see, this file is opened. So we will be seeing this file in a while, but before that we need to run this, right? So if I want to run my like Streamlit app, What will I write? Streamlit run followed by the relative path of my Streamlit app, right? This is the relative path of my Streamlit app, and then followed by this npx local tunnel port 8501. What does this do? It basically creates a local tunnel from my local machine to the Google server where my session is working. So basically what will happen is my Streamlit will be running locally on the Google server. Like basically it will be treating my uh, Google server as my local machine, and over there Streamlit will be running, correct? So if I do this, let's see what happens. And you see we get a few URLs. So I need to first like create my that thing. I need to create my tunnel. Okay. So I get this website where I need to enter my tunnel password, which is basically my IP, right? IPv4. So this is my IPv4. This is not my IPv4. This is the IPv4 for the session, right? So if I click on submit, I'll be redirected to my Streamlit application. And yep, you can see our Streamlit application is running, and yes, we are pretty much on. Streamlit application is on. Now let us see how this works. After that, we will be getting into the code, right? Let me just hit on browse. Let me just take the image that we had taken. This was the image that I had uploaded previously in that online portal, and let's see how our application works. And you can see that my image has been uploaded, and if I hit on process, I will be getting a result, and it is running, and you see this is the result that we had got, right? So if I save this image, right, if I save this image, I save it, and if I go on downloads and check it out, okay, this is not what I want, this is what I want. Yeah, so if I just zoom in, you can see though the picture quality is not very good. Why is the picture quality not very good? Because we had worked with only lesser dimension, that is 128 128. We could have worked with a higher dimension, but that would have required a lot of computational power. But we are not really going with a high computational power. We are just, this is a normal tutorial just to see how we can build our own. If you want to build higher, like high definition or like generators, you can basically work with higher dimensions, but you can see the results are pretty cool. Like the press results are pretty accurate and seems very like original, correct? So now let us analyze the code. Okay, so for the code we will be seeing our Streamlit app.py. Okay, so what does a Streamlit app.py do? First, I need to import Streamlit at st. So Streamlit is basically the library for making web apps pretty easily. And then I need to import what? I need to import my load model from my Keras or TensorFlow, TensorFlow or Keras models. And then I also need to import NumPy and CV2, right? Now let us see step by step what we need to do next, right? Then I'm writing st.title photo to sketch app. What does this do? This basically gives a title to my website. So if you see that what is my title to this website, it is photo to sketch app. This title was given by this like tiny piece of code, st.title photo.sketch app, right? Then what I'm doing is that I'm loading my model, right? I'm using the load model command, and like not the command, like the function, and inside that I'm passing my relative path to the model that I have saved, and I'm storing that model in my model variable. Right now this model is basically, this model holds my AI model, the ML model that I just created, the deep learning model. Then I am writing st.write upload an image and see its processed version, right? So if I go back to my application, the next statement that is written, that is upload an image and see its processed version. This output, this thing that I get is from this tiny piece of code, upload an image and see its processed version, correct? Then I get uploaded image equals st.fileUploader, then followed by choose an image, and then I have mentioned type JPG, JPEG, and PNG. So over here, I am taking a file uploader where I can upload files. And what types am I just choosing? Like what files am I restricting it to? It is only restricted to image files, which are JPG, JPEG, and PNG, right? So if I see after that statement, we had this file uploader section where you can drag and drop your file, and we had restrictions. It was JPG, JPEG, and PNG. And just above that, we had this statement, choose an image. This was given by this caption that we had mentioned, choose an image, right? Now, whatever file you upload gets stored in this variable called uploaded image, correct? So over here, whatever I upload after browse files, whatever thing I click and upload will basically get stored in my uploaded image. Initially, uploaded image is null, like none, like holds nothing. But as soon as you upload something to it, it gets stored, like it has some value, right? So that is exactly what we check next. We check if uploaded image is not none. Like this statement checks that if something has been uploaded, then what I need to do is I need to get hold of my data that is stored in my file. So what will I do? I will write file underscore bytes equals numpy dot as array followed by byte array uploaded image dot read followed by d type equals numpy unary int 8, right? What does this do? This statement basically converts the entire image that I had uploaded into a like entire file that I had like uploaded into a numpy array. Now this numpy array holds what? Now this numpy array holds my image files, my image data, right? So once my image data, like the bytes of my image data, like you know, right, that data is stored in bytes, right? In computers, everything is bits and bytes. So now this file byte stores the data that was inside the file, correct? Now from that file I need to extract the image. How will I do it? I will use cv2, like OpenCV Python, cv2.im decode. Inside that I am mentioning what do I want to decode. I want to decode the file bytes. Once I am decoding the file bytes based on what? I am based on, like I am decoding the file bytes based on cv2.imRead color. Like I'm specifying that whatever you are reading is basically an image. So you need to decode it as an image. Like you need to know that whatever you are decoding is an image. So please treat it as an image and not anything else. Correct? Great. Now after these two statements, I have got hold of my image. Correct? Now, once I've got hold of my image, I will basically do what? My pre-processing steps. My first pre-processing step was resizing my image. So when I write cv2.resize image followed by 128, 128, then followed by interpolation equals cv2.interarea, what does this do? This basically resizes my image down to what? 128 row pixel and 128 column pixel dimensioned image, correct? After that, what will I do? I will normalize my image. I'll normalize my pixel values to the range of 0, 1 using this statement, right? We have already discussed that before, right? Once this pre-processing has been done, I am telling that show me whatever image that you have got, show me. So what do? I write st.image and then I pass image. Now these things, channels equals BGR, captions equals original image, these are optional stuff. These are not required. If you want to mention, you might. If you don't want to mention, no problem. But if you just write st.image and then pass image, it will pretty much display the image, correct? So after this, what did we have? After we had uploaded our file, we had got this image, and under that we had this caption, original image, correct? So that is brought by this tiny piece of code, right? Okay. After that, what we had done is that we had pressed on this process version and then we had got this processed image, correct? So what do I write? If st.button process, what does this mean? First, it means that first create an st.button process, and if st.button process is pushed, like if this st.button is hit, what will happen? st.button process will become true, right? If it is not pushed, then the value is false. So this if block will not get executed, and if this button process is pushed, then it becomes a true value, and this true value will then this if block will get executed, correct? Then what do I need to do? Whatever image I was getting, I had to reshape it back. I had to reshape like by adding a row to it. So basically I'm inserting my image inside a row, right? After that I am passing it to the model, right? I'm writing model.predict image and storing the result in this res variable, right? Once res variable has got the result, I basically need to take out my image from again the row in which I had actually put it in. So basically I have a row in which I put the input image, it processes it and gives the output image inside that same row. I need to take it out from that row. So I will write res equals np.reshape res followed by the dimension, that is 120, 120, 3. So basically what does this do? This basically takes out my resulted image out of the row, right? And once that is done, I'll basically just display my image. I'll just write st.image, then followed by res, then I'll write caption processed image, right? So that is what gives me this result, this, and with this caption processed image. Yes. With this, we pretty much come to the end of this lecture, and with this, I conclude the lecture.